Listening practice, an expanded and refined version of Part I, Introduction to Soil Mechanics Laboratory, with additional subsections for better clarity and depth. Part I, Introduction to Soil Mechanics Laboratory 1. Overview of Soil Mechanics, 1.1 Importance of Soil Testing, Role in Geotechnical Engineering, Applications in Foundations, Slopes, Pavements, and Earthworks, Correlation between lab tests and field behavior. 1.2 Laboratory Safety and Equipment, Personal Protective Equipment, PPE, Handling Hazardous Materials, Chemicals, Heavy Machinery, Calibration and Maintenance of Lab Instruments, Common Equipment List, Sieves, Ovens, Consolidometers, Shear Devices. 1.3 Standards and Codes. ASTM, D698, D854, D4318, etc., AASHTO, T89, T90, T99, etc., BS, BS 1377, BS 5930, is 2720 series. Importance of standardized procedures 2. Soil classification and identification, 2.1 Visual and manual classification, field identification, color, texture, grain shape, organic versus inorganic soils. 2.2 Grain size distribution, sieve analysis, coarse grain soils, hydrometer analysis, fine grain soils, particle size distribution curves, uniformity coefficient. 2.3 Atterberg limits, liquid limit, Casagrande cup, fall cone method, plastic limit and plasticity index, shrinkage limit and its significance. 2.4 Soil classification systems, Unified Soil Classification System, USCS, AASHTO Classification System, Group Index and Engineering Implications. Curvature coefficient, key enhancements. 1 Added practical applications, e.g., link between lab tests and real-world geotechnical problems. 2 Detailed safety protocols, PPE, equipment handling. 3 Explicit standard references, ASTM/AASHTO codes for each test. 4 Visual/manual classification for field relevance. 5 Emphasis on data interpretation, e.g., particle size curves, plasticity chart. Would you like to include case studies or worked examples in this section? Or should we proceed to expand other parts, e.g., Part 2 on soil properties? Here's a detailed expansion of Chapter 2, Soil Classification and Identification, structured for clarity and depth, suitable for a soil mechanics laboratory textbook. Chapter 2, Soil Classification and Identification. 2.1 Visual classification of soils, field identification techniques, color, e.g., dark equals organic, red equals iron-rich, texture, gritty, smooth, sticky, moisture state, dry, moist, saturated, odor, organic soils, hand tests, dilatancy, shaking test for silt versus clay. Dry strength, crushing behavior, plasticity, rolling thread test, organic content estimation, visual cues, fibers, dark color, burn test, ignition loss method. 2.2 Grain size distribution, sieve analysis, for sands and gravels, ASTM D6913/AASHTO T88, procedure, oven drying, sieving, weighing, plotting gradation curves, key parameters, D10, D30, D60, effective size, uniformity, CU, uniformity coefficient, CC, curvature coefficient, hydrometer analysis, for silts and clays, ASTM D7928/AASHTO T88, Stokes' Law Principles, calibration and corrections, temperature, meniscus, combined analysis, merging sieve plus hydrometer data, example, gap-graded soils. 2.3 Atterberg limits, liquid limit, LL, Casagrande cup, ASTM D4318, fall cone method, BS 1377, flow index calculation, plastic limit, PL, thread rolling technique, plasticity index, pi equals LLPL, shrinkage limit, SL, mercury displacement method, volumetric changes versus water loss. Activity of clays, relation between pi and clay fraction 2.4 Soil classification systems, Unified Soil Classification System, USCS, symbols, e.g., GW, CL, MH, flowchart for classification, dual symbols, e.g., SCSM, AASHTO system, group index, GI, calculation, highway material suitability, comparison of USCS versus AASHTO, when to use each system, limitations of classification. Key features of this chapter, 1 step-by-step procedures lab protocols aligned with ASTM/AASHTO/BS. Standards. 2 practical tips. Common errors, e.g., overdrying soils, sieve clogging. 3 data interpretation worked examples for gradation curves, pi calculations. 4 visual aids diagrams for Atterberg tests, USCS flowchart. 5 field relevance links between lab results and engineering behavior, e.g., high pi equals expansive clay. Suggestions for enhancement, add a case study comparing misclassified soils and consequences, e.g., foundation failures. Include troubleshooting tables, e.g., why is my LL test inconsistent? Would you like to integrate sample lab report templates or focus on another chapter next? Part 2, Soil Properties and Testing. Chapter 3, Soil Moisture Density Relations. 3.1 Water Content Determination, Oven Drying Method, Objective, determine the natural moisture content of soil. Standards, ASTM D2216, AASHTO T265, is 2720, Part 2, Procedure, 1 weigh a clean, dry container. 2 add a wet soil sample and record the total mass. 3 dry in an oven at 105-110 degrees C for 24 hours, or until constant mass. 4 cool in a desiccator and reweigh. Calculations, \w, %, equals \frac m_w m_s \times 100 equals \frac text mass of water \text mass of dry solids \times 100 common errors and fixes, overheating, 110 degrees Celsius, alters clay minerals. Incomplete drying, retest until constant mass. 3.2 Specific gravity of soil solids, objective, measure the density of soil solids relative to water. Standards, ASTM D854, AASHTO T100, is 2720, Part 3, Methods, 1 Pavement method, for fine-grained soils. 2 Density bottle method, for coarse-grained soils. Procedure, Pavement, weigh dry soil, \m_s Add water, boil to remove air, and cool. Fill pavement, weigh, \m_pw and measure temperature. Calculations, \g_s equals \frac m_s m_s, m_pw, m_w, \row_w where \row_w equals density of water at test temp. Typical values, quartz sands, 2.65 2.67, clays, 2.70 2.93.3 compaction tests, standard and modified Proctor, objective, determine the optimum moisture content, OMC, and maximum dry, MDD. Standards, standard Proctor, ASTM D698/AASHTO T99, lower energy. Modified Proctor, ASTM D1557/AASHTO T180, higher energy. Equipment, compaction mold, 944 cubic centimeters or 4-inch diameter. Rammer, 2.5 kilograms for standard, 4.5 kilograms for modified. Procedure, 1 Prepare soil at 4-5 moisture contents, dry to wet. 2 Compact in 3 layers, Standard, 25 blows/layer, modified, 56 blows/layer. 3-way, extrude, and sample for moisture content. Calculations, \_D equals \frac \gamma_W1 plus W \quad \text, dry density, plotting results, compaction curve, moisture versus dry density. Zero air voids, ZAV, line for theoretical max density. Applications, road subgrades, embankments, earth dams. Common issues, poor moisture control flattens curve. Overcompaction misleading high density. Density-key features of this chapter, 1 standard compliant, follows ASTM/AASHTO/IS codes. 2 step-by-step lab guides, replicable procedures for students. 3 theory and practice, links equations to real-world compaction. 4 troubleshooting tips, identifies common lab mistakes. Suggested additions, case study, how OMC/MDD affects pavement design. Video demo link, Proctor test demonstration. Would you like to expand Part 3, Advanced Testing, next? Chapter 4, Permeability and Flow Characteristics. Permeability is a critical soil property that governs fluid flow through porous media, influencing drainage, seepage, and consolidation. This chapter covers laboratory methods to determine hydraulic conductivity, K, of soils. 4.1 Constant head permeability test objective, measure permeability of coarse-grained soils, e.g., sands, gravels, under steady-state flow. Standards, ASTM D2434, AASHTO T215, is 2720, Part 17, Equipment, Constant head permeameter, graduated flask, to measure discharge, de-aired water supply, stopwatch procedure, 1 compact soil in a cylindrical mold, avoid layering. 2 saturate the sample slowly to prevent air entrapment. 3 apply a constant head difference, delta H, across the sample. 4 measure discharge, Q, over time, T, at steady flow. Calculations, \k equals \frac QLA \delta H \T equals hydraulic conductivity, cm/s, q equals total discharge, cm superscript 3, L equals length of sample, cm, A equals cross-sectional area, cm superscript 2, delta H equals head difference, cm, keynotes, valid for K10 superscript 3 cm/s, coarse soils. Errors, air bubbles, reduce saturation, side leakage, seal joints properly. 4.2 Falling head permeability test objective, determine permeability of fine-grained soils, e.g., silts, clays, with low flow rates. Standards, ASTM D5856, is 2720, Part 17, Equipment, Falling head permeameter, standpipe with marked graduations, flexible tubing and valves procedure, 1 saturate the soil sample, may take 24 plus hours for clays. 2 record initial head, H, in the standpipe. 3 allow water to flow through the sample, measuring head, H, at time, T. Calculations, \k equals \frac L at \ln left, \frac H underscore 1 H underscore 2 \right, \A equals cross area of standpipe, cm superscript 2, H underscore 1, H underscore 2 equals initial and final heads, cm, keynotes, suitable for K equals 10 to 10 cm/s, errors, incomplete saturation, temperature changes, affects water viscosity. Data interpretation and applications. 1. Permeability ranges, soil type \K cm/s, gravel 1010 superscript 1 sand 10 superscript 110 superscript 3 silt 10 superscript 310 clay 10102. Engineering uses, drainage design, e.g., retaining walls, landfills. Seepage analysis, e.g., dams, embankments. Filter design criteria, e.g., /k_text filter 10 / k_ text soil / common lab challenges and fixes issue solution -- air bubbles in sample vacuum saturation or CO flushing leaks in permeability apply grease to O-rings turbulent flow use lower hydraulic gradients -- case study example problem, a sandy silt layer, /k equals 2 / times 10 / cm/s, underlies a proposed calculate seepage loss per day if the hydraulic gradient is 0.05. Solution, /v equals key equals, 2 / times 10, 0.05, equals 1 / times 10 / text cm/s / text daily seepage equals v / times / text area / times 86,400 / text sec / day / reservoir. Key takeaways, constant head, for fast draining soils, sand/gravel. Falling head, for slow draining soils, silt/clay. Accuracy depends on, sample saturation, temperature control, and head measurements. Up next, Chapter 5, Shear Strength Tests, or expand with field permeability tests, e.g., pumping tests. Chapter 5, Soil Strength and Shear Resistance. Shear strength is a fundamental property of soil that determines its stability under loading. This chapter covers laboratory methods to measure shear resistance, critical for slope stability, foundation design, and earth pressure calculations. 5.1 Direct Shear Test Objective, determine the shear strength parameters, cohesion /C/ and angle of internal friction /phi/ of soils under controlled normal stress. Standards, ASTM D3080/AASHTO T236, is 2720, Part 13, Equipment, Shear Box, Split horizontally, Normal Load Application System, Proving Ring or Load Cell, Dial Gauges, Horizontal and Vertical Displacement, Procedure 1. Sample Preparation, trim soil to fit the shear box, typically 60 × 60 mm or 100 × 100 mm. For sands, pour and compact at desired density. For clays, use undisturbed or remolded samples. 2. Testing, apply a normal stress, e.g., 50, 100, 200 kPa. Shear the soil at a constant strain rate, 0.52 mm/min. Record shear force versus displacement. 3 calculations, peak shear stress, /tau equals /frac pa more Coulomb failure envelope, /tau equals C plus /sigma underscore n /10 /phi /tau equals shear strength, /sigma underscore n equals normal stress, C equals cohesion, intercept, /phi equals friction angle, slope, keynotes best for granular soils, sands, and stiff clays. Limitations, non-uniform stress distribution. Cannot measure pore pressure. 5.2 Unconfined compression test, UCT, objective, measure the unconfined compressive strength, UCS, of cohesive soils, clays. Standards, ASTM D2166/AASHTO T208, is 2720, Part 10, Equipment, Compression Machine, Sample Extruder, Dial Gauge, Axial Deformation, Procedure 1. Sample Preparation, use undisturbed clay, typically 38 mm diameter times 76 mm height. Trim ends flat and parallel. 2. Testing, apply axial load at 12% strain/min, record load versus deformation until failure. 3. Calculations, UCS, /Q_U equals /frac P_ text max A / undrained shear strength, /S_U equals /frac Q_U2 / keynotes best for, saturated clays, no drainage allowed. Limitations, only for cohesive soils, not sands. Assumes /phi equals 0 / total stress analysis. 5.3 Triaxial compression test, UU, CU, CD, objective, measure shear strength under controlled drainage and confining pressure. Standards, ASTM D2850, UU/D4767, CU, CD, is 2720, Part 12, Equipment, Triaxial Cell, Pressure Control System, Pore Pressure Transducer, for CU/CD, Test Types Test Drainage Pore Pressure Soil Type --UU, Unconsolidated Undrained, No Not Measured Saturated Clays, Short-Term Stability, CU, Consolidated Undrained, yes, before shear, Measured Clays, with Pore Pressure Effects, CD, Consolidated Drained, yes, full. Drainage, Zero sands and long-term stability. Procedure 1. Sample preparation, trim soil to cylindrical shape, typically 38 × 76 mm. Enclose in rubber membrane. 2. Consolidation, CU/CD only, apply confining pressure, /sigma_3 and allow drainage. 3. Shearing, apply axial load at 0.52 mm/min, strain controlled. Record deviator stress, /sigma_1, /sigma_3 versus strain. 4. Calculations, Moore's circles for multiple tests. Shear parameters, UU, /S_U equals /frac, /sigma_1, /sigma_3, 2 /CU/CD, /C, /phi from failure envelope. Keynotes best for, all soil types, most versatile. Limitations, complex setup. Time consuming, especially CD tests. Summary of methods. Test soil type, drainage output parameters direct shear sands, stiff clays drained /C, /phi unconfined compression saturated clays undrained /S_U triaxial, UU, clays undrained /S_U triaxial, CU/CD, all soils controlled /C, /phi effective stress, engineering applications, slope stability, /phi from CD tests for long-term safety. Foundation design, /S_U from UU for short-term bearing capacity. Earth pressure, /C, /phi for retaining wall design. Next steps, add case studies, e.g., slope failure due to underestimated /phi. Include troubleshooting tips, e.g., membrane leakage in triaxial tests. Would you like to expand with sample lab data sheets or proceed to Part 3, Advanced Testing? Chapter 6, Consolidation and Settlement Analysis. This chapter covers laboratory methods to evaluate the compressibility and time-dependent settlement of fine-grained soils, clays, silts, crucial for foundation design and embankment construction. 6.1 One-dimensional consolidation test, Oedometer test, objective, determine the compression characteristics of soil under vertical stress. Standards, ASTM D2435/AASHTO T216, is 2720, Part 15, Equipment, Consolidation Cell, Oedometer, Load Frame, Incremental Loading, Dial Gauge, Vertical Deformation, Porous Stones, Top and Bottom for Drainage, Procedure 1. Sample Preparation, Trim undisturbed clay sample, typically 60-75 mm diameter, 20 mm height. Saturate, if required, and place in the consolidometer. 2. Loading sequence, apply incremental loads, e.g., 12.5, 25, 50, 100, 200, 400, 800 kPa. Each load is held for 24 hours, or until primary consolidation completes. 3. Data recording, measure settlement versus time for each load. Plot void ratio, E, versus log pressure, sigma, curve. Key outputs, compression index, cc, slope of the virgin compression curve. Recompression index, cr, slope of the reloading curve. Coefficient of consolidation, cv, from time settlement curves, Taylor's T or Casagrandi's log T method. Common errors and fixes. Issue solution sample disturbance. Use sharper trimming tools. Uneven loading. Ensure proper alignment of load frame. Incomplete saturation. Pre-soak porous stones. 6.2 Determination of compression index, cc, formula, \c_c equals \frac \delta e \log \left, \frac sigma _2 sigma _1 right, where, \delta e equals change in void ratio, \sigma _1, sigma _2 equals effective stresses on the virgin compression line. Typical values, soil type C_C range soft clay 0.2 0.5 medium clay 0.1 0.3 stiff clay 0.1 application, estimate primary settlement in clays, \delta H equals \frac C_CH_01 plus E_0 log left, \frac sigma _0 plus \delta sigma _0 right, \6.3 Pre-consolidation pressure, sigma, definition, maximum past effective stress experienced by the soil. Determination, Casagrandi's graphical method, 1. Plot E versus log sigma curve. 2. Identify the point of maximum curvature, A. 3. Draw a horizontal line, AB, and a tangent, AC. 4. Bisect the angle, BAC, and extend to intersect the virgin curve. 5. The x-coordinate of the intersection is sigma. Significance, over-consolidated, OCR1 soil has been loaded more in the past, e.g., glacial deposits, \OCR equals \frac sigma _P sigma _0 normally consolidated, OCR equals 1 current stress is the highest ever experienced. Engineering implications, over-consolidated clays, lower settlement risk. Normally consolidated clays, high compressibility. Summary table, key consolidation parameters. Parameter symbol. How determine significance compression index C_C / slope of E-log curve predicts long-term settlement. Recompression index C_R slope of reloading curve. Elastic rebound behavior. Coefficient of consolidation C_V time settlement curve. Rate of consolidation. Pre-consolidation pressure \sigma _P Casagrandi's method. Stress history of soil case study, settlement calculation problem, A4M thick clay layer, E_0 equals 0.9, C_C equals 0.3 with current stress sigma _0 equals 50 kPa is subjected to a new load \delta sigma equals 100 kPa \. Compute the settlement. Solution, \delta H equals frac 0.3 times 4001 plus 0.9 log left, frac 50 plus 150 right, equals 126 text dash key takeaways 1. Oedometer test quantifies compressibility under 1D loading. 2 cc and cr predict settlement magnitude. 3 sigma reveals stress history, OCR critical for design. 4 CV determines how fast settlement occurs. Next steps, add lab data sheets for consolidation tests. Discuss field versus lab consolidation differences. Would you like to include secondary compression, C alpha, or proceed to Part 3, Advanced Testing? Chapter 7, California Bearing Ratio, CBR. Test. The California Bearing Ratio, CBR, test is a critical laboratory method to evaluate the strength of subgrade soils and base materials for pavement design. This chapter details the standardized procedure, interpretation, and applications of CBR testing. 7.1 Sample Preparation Objective: prepare soil samples at optimum moisture content, OMC, and maximum dry density, MDD, for testing. Standards, ASTM D1883, AASHTO T193, is 2720, Part 16, Methods of Preparation 1. Static compaction, for cohesive soils, use Proctor mold, 152 mm diameter times 177 mm height. Compact in 5 layers with 62 blows/layer, standard Proctor energy. 2 Dynamic compaction, for granular soils, vibratory hammer or manual rammer. 3 Soaking, optional, submerge sample for 96 hours to simulate worst-case moisture conditions. Measure swell percentage during soaking. Key points: mold size, standard, 152 mm, or smaller, 100 mm, for fine soils. Compaction effort, must match field conditions, standard versus modified Proctor. Common errors: inconsistent layer thickness, uneven density. Improper soaking, unrealistic swell values. 7.2 CBR test procedure: equipment, CBR testing machine, penetration piston, 50 mm diameter. Dial gauges, for penetration and swell measurement. Surcharge weights, 5.5 kilograms for pavement simulation. Step-by-step process 1. Setup: place compacted sample in the mold with filter paper and perforated plate. Apply surcharge weight, simulates overburden pressure. 2. Penetration test: drive the piston into the soil at 1.25 mm/min, record load versus penetration at intervals, 0.5, 1.0, 1.5, 2.0, 2.5, 3.0, 4.0, 5.0, 7.5, 10.0, 12.5 mm. 3. Swell measurement: if soaked, measure vertical expansion during soaking. Calculations: CBR value, text CBR, %, equals left, frac text test load text standard load right, times 100 standard loads, 2.5 mm penetration 13.24 knots, 3000 lbf. 5.0 mm penetration 19.96 knots, 4500 lbf. Report the higher of the two values, usually at 2.5 mm for rigid pavements, 5.0 mm for flexible pavements. Example calculation: penetration, mm, load, kn, CBR, %, dash 2.5 8.5, 8.5/13.24, times 100 equals 64.2%, 5.0 12.1, 12.1/19.96, times 100 equals 60.6%, reported CBR, 64.2%, higher value. 7.3 Interpretation of results CBR classification CBR, percent, soil suitability 3 very poor, requires replacement, 7 poor, needs stabilization, 20 fair, suitable for subgrade, 50 good, base course material, 50 excellent, high quality base, engineering applications 1. Pavement design, used in AASHTO 1993 and IRC methods for flexible pavement thickness. Higher CBR thinner pavement required. 2. Embankment construction, CBR 15% preferred for fill materials. 3. Airfield runways, FAA uses CBR for rigid pavement design. Common issues and solutions problem solution low CBR, 5%, lime/cement stabilization excessive swell, 2%, use non-expansive soils or geotextiles inconsistent results check compaction uniformity case study, CBR in road construction scenario, a highway subgrade has a CBR of 6%. Determine the required granular overlay thickness, as per IRC 37-2018. Solution, for 10 million standard axles, MSA, required thickness equals 600 mm, including subbase, base, and surfacing. Key takeaways 1. CBR measures subgrade strength for pavement design. 2. Soaking simulates worst-case moisture conditions. 3. Higher CBR equals better load-bearing capacity. 4. Standard loads at 2.5 mm and 5.0 mm penetration are critical. Next steps include sample CBR test reports. Compare CBR versus dynamic cone penetrometer, DCP, field tests. Would you like to add modified CBR tests, for soaked versus unsoaked conditions, or proceed to Chapter 8, in-situ testing? Chapter 8, in-situ soil testing methods. In-situ testing evaluates soil properties directly in the field, providing critical data for construction quality control and geotechnical design. This chapter covers 2 key methods, field density tests and the vane shear test. 8.1 Field density tests objective, determine the in-place density and compaction of soils during construction. 1. Sand cone method, ASTM D1556/is2720 Part 28, equipment, sand cone apparatus, calibrated with uniform sand. Excavation tools, chisel, scoop. Balance, for mass measurements. Procedure, 1. Calibrate sand density, fill cone with sand and weigh. Determine sand's unit weight, \gamma_text sand \. 2. Field test, dig a small hole, 15 cm deep, collect all soil, and weigh, \w_text wet \. Fill hole with sand and measure volume, v equals frac w_text sand \gamma_text sand Oven dry soil to find water content, w Calculations, text wet density equals frac w_text wet v, quad text dry density equals frac text wet density 1 plus w advantages, low cost. Suitable for most soils. Limitations, slow for large projects. Unsuitable for soft/loose soils, hole collapses. 2. Rubber balloon method, ASTM D2167, equipment, rubber balloon densitometer. Water-filled cylinder. Procedure, 1. Excavate a hole and measure its volume by inflating a rubber balloon into it. 2. Weigh excavated soil and calculate density, similar to sand cone. Advantages, faster than sand cone. No sand calibration needed. Limitations, balloon may puncture in rocky soils. 3. Nuclear density gauge, ASTM D6938, Equipment, nuclear moisture density gauge, emits gamma rays. Procedure, 1. Place gauge on soil surface or probe into a hole. 2. Measure wet density and water content via radiation scattering. Advantages, instant results. High accuracy. Limitations, expensive. Requires radiation safety training. Comparison of methods. Method cost, speed, accuracy. Best for sand cone, low, slow, moderate. Most soils, rubber balloon, medium, moderate. Cohesive soils, nuclear gauge, high, fast, high. Large projects. 8.2 Vane shear test, ASTM D2573/is 2720 Part 30. Objective, measure undrained shear strength, /S_U/ of soft clays and saturated silts in situ. Equipment, vane shear device, 4-bladed vane, height equals 2 times diameter. Torque measurement system. Procedure, 1. Insert vane vertically into undisturbed soil. 2. Rotate vane at 6 degrees per minute until soil fails. 3. Record peak torque, /T_text max /. Calculations, /S_U equals /frac T_text max K, /quad K equals /pi D2 left, /frac H2 plus /frac D6 right, D equals vane diameter, H equals vane height, K equals vane constant, geometry dependent. Applications, embankment stability on soft clays. Landfill liner strength assessment. Advantages, direct measurement of /S_U/. Minimal sample disturbance. Limitations, only for soft, cohesive soils, /S_U 200 /text kPa / affected by vane insertion speed. Case study, field density control problem, a highway embankment requires 95% relative compaction. Proctor. Nuclear gauge tests show, field dry density equals 1.78 g/cm superscript 3, lab MDD equals 1.85 g/cm superscript 3, per standard solution, /text relative compaction equals /frac 1.78 1.85 times 100 equals 96.2 %quad, /text passes, /key takeaways 1. Field density tests, sand cone, versatile but slow. Nuclear gauge, fast but costly. 2. Vane shear test, critical for soft clay strength. Torque to shear strength conversion is geometry dependent. 3. Standards matter, ASTM/is codes ensure consistency. Next steps, add troubleshooting tips, e.g., nuclear gauge calibration. Discuss correlations, e.g., CBR versus density. Would you like to include lightweight deflectometer, LWD, tests or proceed to Chapter 9, Special Soil Tests? Chapter 9, Special Soil Tests. Certain soils exhibit unique behaviors that require specialized testing. This chapter covers 2 critical tests, swell potential, for expansive clays, and frost susceptibility, for cold region engineering. 9.1 Swell potential of expansive soils. Objective, quantify volume change in expansive clays due to moisture variation. Standards, ASTM D4546, one-dimensional swell/collapse, is 2720, Part 41, Equipment, Consolidometer, Oedometer with swell measurement. Load frame, for constant pressure. Dial gauge, 0.002 mm accuracy. Procedure 1. Sample prep, trim undisturbed clay to fit ring, 60-75 mm diameter. Saturate porous stones. 2. Testing, apply surcharge pressure, e.g., 7 kPa for lightly loaded structures. Flood with water and measure swell, percent, over 24 plus hours, text swell percent equals frac delta HH underscore 0 times 100 optional, repeat under higher pressures, simulating foundations. 3 classification, swell potential percent swell expansion risk low 1% negligible medium 5% moderate high 5% severe mitigation strategies, lime/cement stabilization, reduces plasticity. Moisture barriers, geotextiles, graded filters. 9.2 Frost susceptibility test objective, evaluate soil susceptibility to frost heave in freezing conditions. Standards, ASTM D5918, frost heave/thaw weakening. AASHTO T336, dynamic modulus after freezing. Equipment, frost heave apparatus, temperature controlled. Water reservoir, capillary supply. Displacement sensors. Procedure 1. Sample prep, compact soil at OMC in a cylindrical mold. Saturate from bottom, simulating groundwater rise. 2. Freezing cycle, cool top to 10 degrees C while maintaining base at plus 4 degrees C, 24-72 hours. Measure heave, mm, and water intake. 3. Thaw cycle, warm sample and measure strength loss, CBR or unconfined compression. Classification frost group heave rate, mm/day, suitability F1, low, 0.5 safe for subgrade F4, high, 2.0 requires replacement engineering solutions, non-frost susceptible fill, gravels, coarse sands. Insulation, EPS geofoam. Case study, expansive clay damage problem, a building in Texas cracked due to 8% swell in underlying clay. Solution, underpinning and moisture control, perimeter drains. Key takeaways 1. Swell tests, critical for foundations in arid/semi-arid regions. Swell 3% demands mitigation. 2. Frost tests, govern road design in cold climates. F4 soils must be replaced below frost line. Next steps, add correlations, e.g., plasticity index versus swell. Discuss field monitoring, soil moisture sensors. Would you like lab data sheets for these tests or proceed to Part 4, Data Analysis? Chapter 10, Laboratory Data Interpretation. Proper data analysis ensures reliable geotechnical conclusions. This chapter covers statistical methods and error management for soil test results. 10.1 Statistical analysis of test results. Key statistical tools. Method formula application mean bar x equals frac sum x underscore in average value of test data. Standard deviation, sigma, sigma equals sqrt frac sum x underscore I bar x 2 and 1 data variability coefficient of variation, COV, text COV equals frac sigma bar x times 100 %. Consistency check. Regression analysis y equals mx plus c correlate parameters, e.g., CBR versus density. Example, shear strength data test phi degree 128.5 to 30.23 27.8 mean bar phi equals 28.8 degrees, sigma equals 1.2 degrees, COV equals 4.2%, acceptable if 10%. Outlier detection, Grubbs test, G equals frac vert text suspected outlier, bar x vert sigma if G text critical value reject the data point. 10.2 Error and uncertainty in measurements. Error types. Type cause mitigation systematic calibration. Drift regular equipment checks. Random human/equipment noise. Repeat tests. Gross sample contamination. Training protocols. Uncertainty quantification. 1. Standard uncertainty, \u \u equals \frac text error \sqrt3 quad text for uniform distribution, \2. Combined uncertainty, \u underscore c \u underscore c equals \sqrt u underscore 1 2 plus u underscore 2 2 plus dots \3. Expanded uncertainty, u u equals k dot u underscore c quad, k equals 2 text for 95% confidence, example, Proctor test uncertainty parameter error u mass, g, plus or minus 0.5 0.29 volume, cm superscript 3, plus or minus 2 1.15, u underscore c equals sqrt 0.292 plus 1.152 equals 1.19, u equals 2.38 g cm superscript 3 reporting best practices. 1. Significant figures, match instrument precision, e.g., 1.85 g cm superscript 3, not 1.8532. 2 graphs, include error bars, e.g., compaction curves. 3 metadata, no test conditions, temperature, operator. Case study, erroneous CBR data problem, a contractor reported CBR equals 15%, COV equals 25%. Investigation, found improper compaction in 2/5 samples. Corrected CBR equals 12%, COV equals 8%. Key takeaways. 1. Statistics distinguish noise from trends. 2. Uncertainty analysis defends conclusions. 3. COV 10% indicates reliable data. Next steps, add Excel/Python templates for calculations. Discuss AASHTO's tolerable error limits. Proceed to Chapter 11, Report Writing, or include AI in geotechnical data analysis. Chapter 11, Writing a geotechnical report. A well-structured geotechnical report transforms raw data into actionable insights. This chapter covers professional formatting and effective data presentation for lab reports. 11.1 Formatting Laboratory Report Standard Structure. 1. Title page, project name, client, date. Lab name/test standards, e.g., ASTM D698 Standard Proctor. 2. Executive summary, key findings, e.g., maximum dry density equals 1.92 g/cm superscript 3 at 12% OMC. Urgent recommendations, e.g., expansive clay detected require lime stabilization. 3. Test procedures, reference standards, ASTM/AASHTO/IS. Equipment list, model numbers, calibration dates. 4. Results, tabulated data, avoid raw data dumps, highlight key values. 5. Analysis, compare results to specifications, e.g., field density equals 95% of Proctor MDD. 6. Appendices, raw data sheets, calibration certificates. Style tips, fonts, use consistent serif, e.g., Times New Roman, for body, sans serif, e.g., Arial, for headings. Margins, 1, 2.54 centimeters, on all sides. Page numbers, bottom center. 11.2 Presenting test data, graphs, tables, and charts. 1. Graphs. Best practices, compaction curve, x-axis, moisture content, %. Y-axis, dry density, g/cm superscript 3. Include zero air voids, ZAV, line. Compaction curve, https://via placeholder.com/400x200, text equals moisture plus versus plus dry plus density plus curve, shear strength envelope, plot tau versus sigma with more Coulomb failure line. Common mistakes, omitting axis labels/units. Using 3D effects, distorts perception. 2 tables example, Atterberg limits sample LL, %, PL, %, pi, %, USCS class S1522329 CHS2381820 CL rules, round decimals consistently, e.g., 23.4, not 23.387. Highlight critical values, e.g., pi 25% equals expansive. 3 charts, pie charts, avoid, use bar charts instead. Bar charts, compare categories, e.g., CBR values at different depths. Software tools, Excel, for basic graphs, customize with format axis minor units. Python, Matplotlib advanced users, error bars, regression lines. AutoCAD/Civil 3D, embed soil profiles in cross sections. Case study, poor versus professional reports. Poor report, the soil is sticky when wet. Professional version, sample LL equals 58%, pi equals 32%, ASTM D4318, classifying as CH per USCS. High pi suggests need for moisture control during construction. Key takeaways. 1. Structure matters, follow a logical flow, introduction methods results conclusions. 2. Visual clarity, use graphs/tables to replace verbose explanations. 3. Standards compliance, cite ASTM/AASHTO for credibility. Next steps, include report templates, Word/LaTeX. Discuss peer review protocols. Would you like a checklist for report review or proceed to appendices? Appendices. The appendices provide quick reference tools to support the main content of the book. These include unit conversions, ready-to-use lab sheets, and key terminology for soil mechanics. Appendix A, Conversion tables. Common unit conversions in geotechnical engineering. Parameter SI unit, imperial unit, conversion factor density G/cm superscript 3 lb/foot superscript 3 1 G/cm superscript 3 equals 62.4 lb/foot superscript 3 permeability cm/s foot/day 1 cm/s equals 2834.6 feet/day stress kPa psi 1 kPa equals 0.145 psi moisture content %%, no conversion, example use, a soil density of 1.85 G/cm superscript 3 converts to 115.4 lb/foot superscript 3, 1.85 times 62.4. Appendix B, Sample Laboratory Sheets 1. Proctor Compaction Test Data Sheet Test No. Mass, G, Volume, cm superscript 3, Wet Density, G/cm superscript 3, Moisture Content, %, Dry Density, G/cm superscript 3, dash 1 4500 2124 2.128.5 1.95 2 4700 2124 2.21 10.2 2.01 Notes, highlight OMC and MDD in results. Attach compaction curve graph. 2. Direct shear test data sheet. Normal stress, kPa, peak shear stress, kPa, displacement at failure, mm, dash 50 32 3.5 158 4.2 plot, tau versus sigma to determine C and dash appendix C, glossary of soil mechanics terms. Term definition Atterberg limits water content thresholds, LL, PL, SL, defining soil states. CBR California bearing ratio, measures subgrade strength. Liquefaction loss of strength in saturated sands during seismic shaking. OCR over consolidation ratio, compares current to past effective stress. Permeability, K, soil's ability to transmit water, units, cm/s. Phi, angle of internal friction in shear strength. How to use these appendices. 1. Conversion tables, ensure consistency in international projects. 2. Lab sheets, standardized data recording across teams. 3. Glossary, clarify jargon for students and field engineers. Bonus digital content, download viewable PDF lab sheets at publisherwebsite.com/soilmechanics. Access interactive unit converters. Final notes, cross-reference, link glossary terms to main chapters, e.g., see Chapter 5 for phi determination methods. Laminates, print conversion tables for lab wall mounting. Next steps, add QR codes linking to video demos of lab tests. Include Excel macros for auto-generating graphs. Would you like a combined PDF of all appendices for easy printing?